There is an old adage that says, if you want peace, prepare for war. And in the post-World War II atomic age of mutually assured destruction, the best offense was an impenetrable defense. The 1976 film you are about to see details the rapid development of a sophisticated defense system designed to assure peace. The key to its success lay in the reliability of a relatively new technology, radar. AT&T had been involved in radar development since 1937, when the U.S. Navy asked the company to devote its research arm to this emerging field. Not an unusual request when you consider that radar relies upon the generation, transmission, and detection of radio waves, something AT&T had been working on for the military as far back as 1917. That's when it developed air-to-ground radio technology and produced phone sets like this one for airplane pilots. Throughout World War II, much of AT&T's vast resources were devoted to the war effort. In collaboration with the U.S. military and its allies, AT&T scientists at Bell Labs were able to innovate and advance critical technologies, especially radar. So it was no surprise in 1955 when AT&T was again approached by the U.S. military and asked to commit research and engineering resources to a national defense system. The result was the Ballistic Missile Defense Program, a 20-year sojourn of technological innovation that would ultimately be credited with influencing peace talks between the world's nuclear superpowers. Straight from the AT&T Archives and History Center, here's the story.
This motion picture will show the history of the United States Ballistic Missile Defense Program, what we call BMD. As the Army's manager for this program, I'd like to place BMD and this film in perspective. BMD is a national program managed by the Army for the Defense Department. And Army involvement first began back in 1955 as a natural extension of the traditional Army mission to provide air defense for the United States. BMD has always been a massive technical challenge, characterized by a quite turbulent history. Over the years, it has been the subject of extensive national debate. Critics attacked it on the grounds of technical feasibility, strategic value. But BMD has withstood the test. The program has been most successful. BMD development activities resulted in major advances in technology of radars, interceptor missiles, computers. Strategically, the most important contribution was the program's impact on strategic arms limitation negotiations. Very little question but that the Soviet Union was impressed with the obvious intent of the United States to proceed with a large-scale deployment of the safeguard system. And this led to the successful SALT I negotiations. All who worked on the program can be justly proud of its accomplishments and its usefulness in establishing a sound design base for future defense systems. Although the safeguard system has been deactivated, the Army and the BMD team are continuing their vital research and development work to assure that the United States retains leadership in this complex area of defense technology.
Ballistic Missile Defense Site. Its location, the northeast corner of North Dakota. Together with the Ballistic Missile Defense Center in Colorado Springs, it constitutes the safeguard system. Its purpose? To defend a portion of our Minuteman ICBM installations against a ballistic missile attack. The Safeguard site in North Dakota was the culmination of 20 years of anti-ballistic missile development. The major phases of ABM development, starting in 1955, were an initial research and development period. Then, programs identified as Nike Zeus, Nike X, Sentinel, and finally, Safeguard, each one building on the shoulders of its predecessor. The number of people involved in this ABM effort reached a peak of over 50,000 in mid-1972. The Army industry team provided not only the technical skills needed to produce the complex components of the system, but also the management and systems expertise to pull it all together. This was indeed a significant challenge. Our nation's defense against ballistic missiles had its roots earlier in aerial defense against bomber threat. In the early 1950s, Nike Ajax was an effective weapon against aircraft which could carry the A-bomb. To counter the developing threat during the mid-1950s, the defense was improved with Nike Hercules, effective against higher speed, higher flying jet bomber formations. Each system used an expendable missile, radar controlled from the ground to the target. The technique is called command guidance. By 1955, the intercontinental ballistic missile, capable of carrying a nuclear warhead, was under development. It could fly thousands of miles in minutes. The warhead's destructive power was beyond comprehension. The nation needed a defense to counter this awesome threat. The Army, Western Electric, Bell Laboratories, and Douglas Aircraft had gained much experience in developing Ajax and Hercules. In 1955, the Army called on the same team to initiate studies for an anti-ballistic missile system. The result? A concept for ballistic missile defense, which was proposed to high-level Army and Department of Defense committees. The first ABM defense system was called Nike Zeus. Here's the way it worked. This is the threat, an ICBM warhead, 1,000th the size of a bomber. Its speed, 4 miles a second. In the Zeus system, an acquisition radar detected, acquired, and tracked the target and continuously fed information on its location to a computer in a defense center. The computer assigned the target to a battery. The computer further assigned the target to a target track radar. Using continuously updated information, the computer determined when to launch an interceptor missile. A missile track radar guided the Zeus missile toward intercept. The computer sent a signal by way of the MTR to detonate the interceptor's warhead at the precise moment to destroy the target. Less than 3 minutes elapsed since the enemy ICBM was detected. 30 minutes since it was launched from 5,000 miles away. The Zeus system was intended for nationwide deployment as either an area defense or defense of ballistic missile launching sites. Early in 1957, the Army gave the go-ahead to the industrial team to initiate R&D effort. At this time, little was known about missile development behind the Iron Curtain. Then, on October 4th, 1957, Russia launched Sputnik 1 into orbit, demonstrating a proven ICBM capability. This added further urgency to the Zeus program. The Army Rocket and Guided Missile Agency was given command of the project, and Bell Labs was given full system responsibility. Western Electric and BTL, as prime contractors, directed the efforts of major subcontractors and hundreds of additional suppliers. The Army required that the development be conducted in such a way that whenever authorization was given, the system could be deployed within 5 years. Work proceeded rapidly on the Zeus program. Many technological advances were required in radars, data processing, and the missile. The system required several radars, each in its own way to have unprecedented capabilities. Innovative focusing lenses, reflectors, huge bearings. All kinds of parts, large and small, had to be fabricated to precise specifications. The transistor, a Bell Labs invention, was a major contribution to data processing. A special transistor developed for Zeus computers made possible significant advances in overall reliability. A telephone manufacturing technique, wire-wrapped connections instead of soldered joints, also improved computer reliability. Use of large-capacity, solid-state computer hardware arranged in modular configuration facilitated manufacture, simplified maintenance, and minimized costs. Douglas Aircraft was responsible for the long-range Zeus missile. The first stage motor produced almost 500,000 pounds of thrust. The most powerful solid propellant motor yet developed. Fins on the jet head steered the missile within the atmosphere, while exhaust gases expelled through the fins steered the jet head outside the atmosphere. To prove in hardware and system designs and to provide the means for gathering data on re-entry phenomena, Nike Zeus equipment was installed at test sites from Ascension Island in the Atlantic to the Kwajalein Atoll in the Pacific. In 1959, Kwajalein was selected as the final test site because it would allow full Zeus system tests against ICBMs launched from California starting in 1962. It already had a concrete landing strip and a fine harbor, which were ideal for the vast amount of equipment that had to be shipped in order to assemble a fully integrated Zeus system. Even so, much had to be done to transform a naval station into a proving ground for the world's most sophisticated ABM technology. The first major Zeus system tests would be at White Sands Missile Range, New Mexico, because of the unique launch-to-impact instrumentation here and the ability to recover missile parts after firing. In 1958, the Army Corps of Engineers contracted for and supervised site construction, preparing the way for the installation and proving in of Zeus components. The system's acquisition radar consisted of separate transmitting and receiving equipment. The receiving antenna used a Lüneburg lens constructed of thousands of polyfoam blocks containing tiny metal slivers. Return signals were focused by the lens on the rotating arms containing receiver equipment to acquire and track targets in 3 dimensions. Its unique feature was its ability to continuously track targets while simultaneously searching 100 million cubic miles of space at a high data rate. Standing some 8 stories high, the receiving antenna rotated in synchronism with the transmitting antenna. Installation of the target track and missile track radars would soon follow. The first target track radar was installed at Bell Labs Whippany to provide a local prototype for proving purposes. In 1961, the Whippany model, encased in its inflatable radome, tracked the Echo satellite at distances up to 2,300 miles, and later successfully received a signal bounced off the moon. Concurrently with these activities, the Ascension Island TTR was installed, and tracking tests began early in 1961. ICBMs were being launched from Cape Canaveral toward Ascension. They provided the first opportunity for gathering information on the flight and breakup characteristics of U.S. missiles as they re-entered the atmosphere. During the same period, under BTL direction, AVCO engineers used highly sophisticated airborne optical equipment. The Ascension re-entry studies provided valuable information on acquiring ICBMs and about ways to discriminate between warheads and other objects. The data were given to both Zeus program and offensive weapons designers. Meanwhile, activity was continuing at White Sands. The Zeus system presented many challenges. For example, during early missile flights, excessive aerodynamic heating of fin control surfaces and their shafts caused failures. One of the advantages of launches here was that missile parts could be recovered for analysis. As problems arose, they were resolved by design modifications. Firings continued until the end of 1963. The last 7 firings were completely successful. A significant achievement was the intercept of a Hercules missile by a Zeus missile on 2 different occasions. During Zeus development, offensive missile weaponry continued to evolve. Discriminating between a warhead and other objects became increasingly difficult. It became clear that in order to accomplish this, a separate discrimination radar would be needed. One unique feature was the radar's movable subreflector to increase the width of the beam to maintain coverage as the target complex approached. In mid-1963, during the final months of tests, White Sands had a distinguished visitor.
What progress you make, what dedication you demonstrate, makes a significant difference to the security of our country and to those who depend upon us. That is an almost unique role to play, and I know that you feel the same sense of pride in your chance, in your time, in your day, to play a part in the life of the great republic, as do all of us whose responsibilities are somewhat different. I want to express my thanks to all of you. We admire what you're doing, and even more important, we're very grateful to all of you. Thank you.
Full system tests would soon start here at Kwajalein against ICBM targets. Many Kwajalein facilities had been enlarged and improved for the influx of Army and civilian personnel and their families. A hospital, schools, and all the necessities of a typical small town were available. At its peak of activity, Kwajalein became a community of about 5,000 inhabitants. The Army officially announced establishment of the Kwajalein Missile Range on October 1st, 1960. Beginning in 1961, some 60 system tests took place. Zeus missiles were fired singly and in salvo. Of particular importance was the free world's first intercept of an ICBM. The target would be launched from Vandenberg Air Force Base, California, some 4,300 miles from Kwajalein. On Kwajalein, the Zeus system was ready to be put to the test. At Vandenberg, an Atlas ICBM lifted off through a heavy fog. On Kwajalein, the Zeus system, after acquiring the target, had less than 3 minutes to track it, determine a point of intercept, and to launch the interceptor missile. The white spot is the target. Zeus will come in from the left. A spotting charge was carried aboard Zeus's 3rd stage. The photography is repeated. This first successful ICBM intercept occurred in December 1962. 9 completely successful intercepts took place. By 1963, the USSR had accelerated its missile programs. The Russians had deployed ICBMs far larger than anything in the United States arsenal. There was also a concern that Russia could soon develop the ability to launch ICBM warheads with decoys in such numbers that their simultaneous arrival would saturate the Zeus defense system. The Department of Defense accordingly decided in 1963 not to deploy Nike Zeus, but to give priority to continue R&D efforts by the same civilian contractor team to develop advanced radars, missiles, and data processing equipment to cope with the expected future threat. The new program was named Nike X. Basic research on reentry phenomena would continue, including the use of Zeus radars at Kwajalein for gathering discrimination data. Nike X would have a radical new approach to radar design. Fixed antennas using electronic beam steering would replace rotating antennas. Since 1960, experimental efforts had indicated that this new concept, called a phased array radar, could perform a multifunction role and provide a major advance in handling simultaneously the many targets of the anticipated high traffic threat. Studies led to the installation of a new kind of radar at White Sands. The advanced radar prototype was to prove that the functions of the Zeus radars, acquisition, discrimination, missile track, target track, and its data processing function could be accomplished by a single radar. This prototype was called MAR-1. It had one face for transmitting, one for receiving, and was capable of moving the antenna beam in a millionth of a second, scanning any sector of the sky many times faster than Zeus radars. Phased array radars can be hardened better against nuclear effects. However, as a result of further MAR studies, it was decided not to deploy a single very powerful phased array radar, but rather two phased array radars which could adequately perform their required function at lower total cost. They were a perimeter acquisition radar, or PAR, for long-range target tracking, and the missile site radar, or MSR, for both target tracking and interceptor guidance. Test information obtained from the MAR studies led to the development of tactical radars. The first was the MSR, tested at the Kwajalein Atoll on Mek Island. Here, assembly had begun in 1966 on the prototype two-face MSR, its associated missile site data processor, and the launch complex for testing tactical missiles. It became clear that threat sophistication had evolved to a point where some warheads, because of their accompanying debris and decoys, could not be distinguished in time to be engaged by the long-range interceptor. A close-in terminal defense was needed. The answer? A new missile called Sprint. It would be so fast that it could rise to a successful intercept, even if launched after low-altitude aerodynamic target discrimination. In flight, Sprint would become incandescent. Its development required major technological breakthroughs. Sprint is gas ejected from its underground cell. Because of its very high acceleration rate, the missile had to withstand unprecedented G stresses. Sprint was developed by the Martin Marietta Corporation, Orlando, Florida. Special coating materials dissipate heat as they ablate and thus limit temperature rise in the missile structure and components. Developmental flights were conducted at White Sands. Not all were successful. It was, after all, a missile whose performance requirements presented staggering demands. However, recovery and examination of flight hardware revealed causes of failures. Isolating and correcting the defects led to a series of spectacular successes. Computers for the Nike X system of vastly increased speed and capacity, achieved with a multiplicity of processors, were developed and tested at Bell Labs Whippany as a team effort with UNIVAC. Ultimately, the multi-processor approach would deliver a computing speed of over 20 million instructions per second. For sites requiring less capacity, the modular design provides the necessary flexibility to meet requirements. One notable achievement in advancing computer technology was Bell Labs' development of an integrated circuit package, or ICP, manufactured by Western Electric at Allentown, Pennsylvania. Hundreds of thousands of ICPs would be required. In the same computer space as before, ICPs provided greater reliability and more than 15 times as much data processing capability as the Zeus modules. ICP manufacturing techniques exemplify the continuing effort to reduce cost. Western Electric enlisted the support of RCA, Motorola, and Texas Instruments in order to meet the planned production volume. ICPs are mounted on chassis. Each chassis contained as many as 1,000 logic circuits. Connections were automatically wire-wrapped. For Nike X, the Zeus missile was modified to increase motor performance and to permit the use of a larger warhead. It was renamed Spartan. Spartan would provide early high-altitude intercept beyond terminal coverage of Sprint. Initial test flights were conducted at Kwajalein. Bell Labs developed and Western Electric manufactured the electronic guidance packages for both Nike X missiles. Early in the development of the ABM program, it was recognized that system hardware had to be able to survive nuclear effects. Hardening tests had been taking place over a period of years beginning in 1959. At the Suffield Test Range in Canada, shaped explosive charges were used to simulate blast effects of nuclear weapons. System components were exposed to other forms of simulated nuclear effects, such as radiation from neutron, gamma rays, and X-rays. Components were also subjected to underground nuclear tests. At this time, reports indicated that the USSR had made further strides in their long-range missile and nuclear arsenal. In addition, 1964 witnessed the first detonation of atomic weapons by the People's Republic of China. Two years later, the Red Chinese would demonstrate a thermonuclear capability. In San Francisco, Secretary of Defense McNamara made the following announcement.
Further, the Chinese-oriented ABM system would enable us to add as a concurrent benefit the defense of our Minutemen systems, and this at a modest cost. And finally, such an ABM system would provide protection against accidental launch by any nation possessing nuclear weapons. Such accidental launches are highly improbable, but they're not inconceivable. After a detailed review, then, of all of these considerations, we've decided to go forward with this Chinese-oriented ABM system.
This system was designated Sentinel. A 17-site deployment was authorized to provide an urban area defense. This is the way the new system would work. The first line of defense is the PAR, the surveillance radar which detects and tracks incoming objects at very long ranges. The PAR and its data processor continuously provide long-range filtered information to the MSR. This radar provides more precise data on the incoming missile. With its own data processing system making computations in millionths of a second, the MSR can select targets and give the command to fire interceptor missiles. First to be launched would be Spartan. Under constant control and guidance by the computer, Spartan soars to intercept above the atmosphere. For intercepts of closer-in targets, the smaller, quick-response Sprint missile is used. The MSR is also capable of controlling Sprint missiles located as much as 25 miles from the radar to provide greater area coverage. These sites contain only Sprint missiles, which are launched and guided via communication links with the MSR. The interceptor warhead needs only to be detonated in the vicinity of the threat to neutralize it. In April 1968, the Sentinel production contract was signed. It was the first anti-ballistic missile system on which a decision to deploy was made. Preparation actually began on the planned first PAR near the greater Boston area. Work on this site would be of short duration. As the ABM program developed, so it seems did opposition to its very existence. From the beginning, the program was controversial. In 1969, with a change in administration, came a review of our national defense policy. President Nixon said,
"After long study of all of the options available, I have concluded that the Sentinel program previously adopted should be substantially modified. The new program that I have recommended this morning to the leaders and that I announced today is one that perhaps best can be described as a safeguard program."
This redirection reduced the 17-site urban area defense to a potential 12-site concept to defend our offensive forces. The Boston area site was discontinued. The initial effort was directed to 4 prime sites, with work to start immediately in North Dakota and Montana. This would constitute the first phase of safeguard deployment. Like Zeus, the safeguard program would be a country-wide effort directed by the United States Army. Safeguard utilized a system manager concept established during the Sentinel program. The system manager reported directly to the Army Chief of Staff with unprecedented authority to manage resources and to direct other Army agencies involved with BMD requirements. Western Electric continued as prime contractor, with Bell Labs responsible for research, design, and development. The major subcontractors were already established with their many suppliers. The Western Electric Safeguard Project Office was established in Greensboro, North Carolina. Here, the vast industrial team effort was coordinated. Although designated prime contractor, Western subcontracted work, representing more than 60% of all system funding. When Safeguard was committed to production, the subcontractors were quickly brought aboard for the design and manufacture of system components. Delivery schedules were established. Designs developed during the R&D program made it possible to start immediately on production on much of the tactical hardware. Western personnel also developed and conducted training programs for Bell system technicians and installers who were assigned to the tactical sites. Among the first actions under Safeguard was to begin work on the sites in Montana and North Dakota. The Corps of Engineers was responsible for site design and building construction. The PAR installation here in North Dakota would be used for R&D tests initially, and later would become the tactical PAR. Meanwhile, system testing had been taking place at Mech Island. The proving in of the MSR design with its associated software as an operational phased array radar presented a tremendous challenge. Systems designers sent to Mech on rotational assignments were able to carry complete knowledge of the design intent to the field. When they returned to their stateside laboratories, they were equipped to contribute a more practical understanding of operating problems and their solutions. Polaris IRBMs launched from a Navy surface vessel, and Minuteman ICBMs launched from California were used as targets for the Mech system tests. Intercept exercises used Spartan and Sprint. In this typical intercept exercise, the re-entry vehicle comes in from the right. The photography is repeated using stop motion. Because of its speed, the incandescent re-entry vehicle appears to be elongated. Illegini Island is about 19 miles across the lagoon from Mech. Sprint missiles were also launched from here. These exercises demonstrated the system's ability to control Sprint interceptors launched from a remote location. The Mech Island test program was concluded in April 1975. Valuable data obtained by the MSR on incoming targets were made available to the Air Force and other agencies responsible for U.S. offensive missile development. During its 5-year span, all objectives were fulfilled. Some 150 intercepts and tracking data missions were conducted with about 90% success rate. The last 21 missions were completely successful. During the entire Kwajalein effort, most of the missions were observed and recorded by personnel and equipment on Russian ships. The Soviet Union thus stayed fully aware of the progress and success of safeguard tests. However, Safeguard comprised more than intercept tests and site installations. In order to develop and test computer programs required for the Safeguard system, the Tactical Software Control Site, or TSCS, was established at Madison, New Jersey. The design and implementation of these programs are considered to be one of the most challenging and complex accomplishments in the history of data processing. Testing began in November 1971. Threat inputs not attainable in the field could be introduced at this facility to verify system capability. Bell Labs and IBM software designers and programming specialists shared in the effort of developing tactical computer programs for the MSR and PAR. The government contracted for the installation of the Ballistic Missile Defense Center, or BMDC, inside Cheyenne Mountain near Colorado Springs as a part of the North American Air Defense Complex. BMDC would be the link between NORAD and the safeguard sites. Communication links between the site and NORAD traverse 2 routes, separated for survivability. Microwave towers transmit wideband data signals to this hardened antenna atop Cheyenne Mountain. After receipt of presidential authority for the release of nuclear weapons, NORAD, through its Combat Operations Center, grants authority to BMDC to launch safeguard missiles. Site preparation in North Dakota was progressing on schedule in order to be ready to receive the large complex assemblage of equipment, including some 1,700 major units and thousands of antenna elements. For PAR to withstand nuclear shock, over 8,000 tons of steel reinforcing bars and more than 58,000 cubic yards of concrete were required. A tunnel connected the radar to a power plant capable of supplying enough electricity for a city of 40,000 population. At the MSR site, massive use of steel and concrete was also made on the radar and its supportive underground building and power plant. Adjacent to the MSR, the Spartan and Sprint missile farms were taking shape. The main portion of the MSR building would be below the surface, much like an iceberg. Only its turret, housing its 4 array faces, would protrude about 80 feet above ground. Meanwhile, production of safeguard components was in full swing. Raytheon plants in Massachusetts were busy manufacturing items for the MSR. Antenna elements, high-power hardware, transmitter and receiver equipment racks, display consoles and other electronic components. All were fabricated to exacting specifications and checked out thoroughly before shipment to the site. General Electric, Syracuse, New York, was responsible for the design and development of the PAR. Although only limited engineering models had been assembled for tests at GE, design studies established during the Nike X period enabled Bell Labs to proceed rapidly with finalizing the PAR design requirements. Missiles and their associated launch hardware and subsystems produced by the Martin Marietta Company and the McDonnell Douglas Company would soon be headed for their waiting silos at the tactical sites. All items were subject to stringent quality control. All production and installation schedules were met. Langdon and Cavalier, North Dakota, are 2 of the farming communities located near the ABM site. They were surveyed by the Army to assess their ability to absorb the influx of safeguard personnel required for the installation and operation of the North Dakota site. The government authorized community assistance funds to expand hospital facilities, schools, police and fire protection, water and waste disposal systems, and road improvements. One of the immediate problems was housing. Western Electric contracted for the fabrication of furnished modular apartment complexes. Single and double-wide trailers were provided by the Army and Western Electric. At the 430-acre complex housing the missile site radar, facilities were made available by the Army for military and key civilian personnel assigned to the site. Family housing, bachelor quarters, a dispensary, a post exchange, a gymnasium, and a base chapel. All were part of the only new Army base installed since World War II. However, events in Moscow had a profound effect on Safeguard. On May 26, 1972, President Nixon met with Soviet leader Brezhnev in the Kremlin. There, they signed agreements to limit offensive and defensive weapons systems. Under the terms of the agreements, the United States and the USSR were each permitted to deploy 2 ABM sites, one protecting an offensive missile site, the other to protect the National Command Authority location. The SALT agreement brought about reorganization of the Safeguard program. Safeguard was now a 2-site effort. However, in accordance with the SALT agreement, all work on the Montana site was discontinued. The site was dismantled, and where feasible, the terrain was restored to its original contour. In addition, Congress decided not to deploy a site to defend the National Command Authority at Washington, D.C. Thus, Safeguard was limited to a single site in North Dakota. In spite of the severity of North Dakota winters, including long periods of sub-zero temperatures and record blizzards, work continued at the Safeguard site. Tactical hardware installation began in 1972. Special all-weather facilities allowed schedules to be maintained. Over 6,000 antenna elements were mounted in the PAR face. Some 250,000 feet of coaxial cable connected the elements through the 7-foot thick face to corresponding electronic components inside the building. Many of the rooms housing critical equipment had to be shock-mounted to survive in a nuclear environment. The PAR faces north, scanning the polar region. Early in 1974, this radar began a series of highly successful satellite tracking exercises, thereby verifying its ability to track a number of targets simultaneously. 30 to 40 satellites can be tracked at a time, with up to 8 targets displayed. The PAR is capable of tracking a satellite object with a radar cross-section as small as a baseball. The 4 faces of the MSR contain more than 20,000 antenna elements. Behind each face stands a feed horn, used to transmit signals to and receive signals from the antenna. Processing equipment transforms the received signals into digital form used by the data processing system to control the equipment involved in an engagement. A total of 100 safeguard missiles would be installed in accordance with the SALT agreement. Sprint missiles were also installed at the 4 remote missile fields. A major milestone was reached late in September 1974 when the safeguard system was officially turned over to the United States Army 3 days ahead of the equipment readiness date, which had been established almost 5 years before. To mark the occasion, brief ceremonies were held simultaneously at the BDMC, Colorado, and here at the North Dakota Safeguard Complex. The Army accepted the system from the prime contractor who acted in behalf of all participating companies. The site was dedicated honoring Lieutenant General Stanley R. Mickelson, the first commanding general of the Army Air Defense Command. Upon successful completion of a rigid technical proficiency inspection conducted by the Inspector General's office, the system was certified for its nuclear mission. This certification permitted the reception and installation of missile warhead sections. The final milestone was reached in April 1975, when the government accepted full control of the North Dakota complex. The system was on a round-the-clock, 7-day-week schedule with daily exercises of the complete system.
Roger.
We have a threat detected. BTD, MTD. Exercise in progress.
Test site readiness level battle stations has been attained.
I currently show complexes 4001 through 4005. I now show complex 4006, SLBM. I show a Sprint and a Spartan in flight.
BTD, this is MTD. Farm status safe. System is restored.
During the first 10 months of its operation, the site had a systems availability of 99.3%. The success of the Safeguard program is recognized by the Honorable Norman R. Augustine, Undersecretary of the Army, during the ERD ceremonies at the North Dakota site.
The country will reap the benefits from spin-offs of this effort well into the future. You introduced unique manufacturing techniques, unique testing, construction procedures, and unique approaches to installation. You developed the Sprint missile and the Spartan missile, whose test track has been phenomenal, to say the very least. The software is of a level of magnitude and complexity equal to that which carried our astronauts to the moon and back safely. These are but a few of the achievements that are represented by the work that you have done here. I believe, without doubt, that the ABM treaties and the interim offensive agreements with the Soviet Union would never have materialized had it not been for the major technical lead that we held over the Soviet Union because of your efforts. In short, the benefits are in terms of peace for people throughout the world. That's the payoff.